Okay, welcome to Module 4. In Module 4, the topic is going to be Chapter 4 in your textbook, which is entitled The Origin of Modern Astronomy. And it's kind of like a history lesson, and you may think, well, gosh, what's history doing in an astronomy course? But as you'll discover in astronomy as well as in many sciences, they are kind of cumulative. One idea is prevalent for a long time until it gets superseded with a new idea. And that's essentially what I want you to get out of it. Don't get too focused on names and dates and names of books and all that kind of stuff. You know, the names are going to be sort of important because it is important to understand who knew what at what time, and then who came up with a new idea and superseded that previous way of thinking. One thing I also want you to appreciate as you read through this chapter is that new ideas didn't just supersede because that person was popular or because that person had money or whatever. It was because that person had evidence. They had new ideas, but those new ideas were backed up with evidence and were able to overturn a previous way of thinking. So pay close attention to that. And as far as mathematically, what I really want you to appreciate is near the end of the chapter, you're going to start to learn about things that Johannes Kepler discovered. He actually put math to astronomy, and he was able to come up with his laws of planetary motion. Make sure you know those laws of planetary motion and how to apply them. And that's part of the lab activity. So between what you read and what you do in the lab activity, that should give you a lot of practice with Kepler's laws of planetary motion. You should also become quite familiar with Newton's laws of motion, as well as Newton's law of universal gravitation. Again, these are mathematical descriptions of how things work, and though that math still works today. So that's why that stuff is really important, is because this is stuff that they discovered hundreds of years ago, and it's still applicable when NASA sends space probes out to rendezvous with a comet. They're using essentially the same orbital mechanics that Kepler and Newton figured out hundreds of years ago. That's pretty awesome. So again, don't get too wrapped up in dates, but sort of appreciate the succession of ideas, as well as pay close attention to Kepler and Newton near the end. So for centuries, people thought that the universe was geocentric, meaning that the Earth, geo, was at the center of all things. And for good reason, because again, that's the way things appeared. They'd wake up in the morning and they'd see the sun rise, and the sun would appear to move through the sky around the Earth. They'd see the same thing with the stars and the moon and the planets. That made sense in this because that's the way things looked. Now there were ideas that the Earth was not the center of all things, but the ancient astronomers kind of discounted that because they said, well, gosh, first of all, yes, the sun, all these planets, they're moving around us. That makes sense. As well as if the Earth were moving, the idea was that you would have a parallax effect. And the parallax effect is, if you hold your thumb out at a wall and you close one eye, the thumb appears to be at one location. You change eyes, and your thumb appears to move. Well, that was the idea that the ancient Greek astronomers, or thinkers, they weren't technically astronomers at this point, but they said, well, gosh, if the Earth was indeed moving, then the constellations should look different. If the Earth were moving its position in space, the constellations should change their shapes over the course of a year. Let's say the Earth was moving around the sun. Wouldn't, just like you blinking your eyes or changing eyes for your viewpoint, wouldn't the Earth in its orbit around the sun essentially change its perspective on the constellations? So shouldn't the Big Dipper look different during the course of a year? Or Orion, wouldn't it look different during the course of the year? What they didn't realize, and they had no way of realizing it, was that the stars that they were referring to are so far away that the small motion of the Earth around the sun has no impact on the shapes of the constellations. Not that there is no parallax effect, but the parallax effect is so small that it can't be detected with the human eye. Again, the quiz app is giving me some trouble, so I'm just going to kind of narrate these preliminary quiz questions. Again, later on in the module, you're going to wind up with some, or later on in this mix, You're going to see some questions that I won't give you the answer to, but these I don't mind giving you the answer to. Hopefully you read this actually in the first page of the chapter. It talks about the idea of the perfect heavens. The heavens were thought to be perfect, meaning two things essentially, meaning that all things moved in perfect circles. So everything that was going around the earth was moving in perfect circles. That was one idea of perfection. And then it was changeless as well. Things wouldn't change. They've always done this. They will always continue to do this. Perfect circles. And that things moved, as part of that perfection, was that they moved at the same speed all the time. So it wasn't like they changed speed. All these objects moved with the same speed. Now, the two things that were not part of this perfection were obviously the Earth, because the Earth constantly was changing. So it was not perfect and unchangeable. It was constantly changing. There was riverbeds that were cutting new paths. There was volcanoes that were, even the ancients could observe this stuff. So they knew the Earth was changeable and therefore not perfect. Likewise, the moon was not perfect. Just by looking at the moon, it's close enough, you could see the fact that it was kind of blotchy. It wasn't a uniform sphere. It had blotches to it. Perhaps with the naked eye they could pick out some craters. So the moon and the Earth did not appear to be perfect, but everything else was assumed to be perfect, meaning changeless, moving in circular orbits as well as moving at uniform speeds. Okay, so the geocentric model of the universe means that, again, the Earth is at the center of all things, and that all the heavenly objects that are moving around the Earth, and they appear to move. I'm going to change my color here. Let's go red. They appear to be moving, in this direction. And the farther away the object, the more significant, or the less significant its motion. So, the sun was thought to be in a shell that's kind of around the Earth. Here's your background stars, also moving. And one thing that the ancients had a hard time dealing with was the fact that, yes, the planets do appear to be moving with respect to the background stars, but occasionally they tend to reverse direction, or at least slow down. And that's a little bit difficult to deal with, especially if you're using the idea that these objects should be moving at uniform speeds. And therefore, for something to appear to slow down is kind of tough to deal with. So what Ptolemy introduced was the idea of epicycles. He explained this slowing down and sometimes even reversal of direction by creating circles within circles. So for instance, he imagined that Mercury was on an epicycle that was essentially centered. So this is the little epicycle that it's a little ring that's going around, but then at the same time, that whole ring is going around this general orbit around the Earth. So it's kind of going on this extra little loop as it goes around its main loop. And this helped to explain, it was his mathematical device, or his geometric device, to explain his observations. He was seeing this, what appeared to be non-uniform motion in the planets. And the way he worked it out was he introduced the possibility of epicycles. Okay, to illustrate this Ptolemaic idea of epicycles, I wanted to use the simulation. And this simulation includes the Earth, that's the blue dot. And you've got Venus, that's the white dot, white and gray dot. And then, of course, you got the sun. And, of course, one thing we'll notice is that the sun winds up creating a lit up side of Venus and a lit up side of the Earth. Now, Ptolemy's challenge was the fact that he noticed that Venus appeared to not be in a uniform speed, constantly going around the Earth in a perfect circle. It appeared to slow down, even reverse direction with respect to the sun. That's a problem. So what he did was he introduced this idea of epicycles, the fact that there's like a circle within a circle, that the Earth, that Venus was going around the Earth on what's called the deferent, but it was also going on an extra loop called an epicycle. And this helped him to explain this apparent slowing down and reversal of direction. Unfortunately, he wound up laying a trap for himself that wouldn't become apparent until hundreds of years later. But because during Ptolemy's time, they didn't have telescopes, and therefore Venus just looked like a dot in the sky, just looked like a very bright star, just like it does to you and I with our naked eye vision. You can't see anything about phases, but it turns out that hundreds of years later, when viewed through a telescope, Venus goes through phases, and that winds up laying the trap for Ptolemy. So let me go ahead and just start the animation and show you what's going on. So as we see, Venus appears to be moving kind of in one direction with respect to the sun. Then it appears to move in the other direction with respect to the sun. Then it kind of slows down and almost comes to a stop in its position with respect to the sun. And then it winds up continuing in the same direction as the sun for a while, slowing down, and then appears to be moving in the opposite direction of the sun. So again, this is what Ptolemy was observing when you looked at that little dot in the sky. And so essentially his epicycle seemed to work. It helped, it was not super pretty, but geometrically it worked. It explained his observation. The problem is when it comes to phases, because notice what you're seeing in that telescope view is that no matter where you're at, even here, when Venus is essentially halfway between the Earth and Sun, and it's on one side of its epicycle, at maximum, it's only not quite halfway lit. It's in a crescent phase, right? Watch that. You know enough about moon phases at this point. Watch how much of Venus gets lit up using this geometry. At most, it is a crescent. It never even gets to being a full quarter Venus. It is either new Venus, crescent Venus, and nothing else. There are no gibbous Venuses. There's no full Venus when it comes to Ptolemy's geometry and epicycles. Okay, I may give you a second to pause the video if you want and actually answer this question before I give you the answer, but it should be pretty apparent, especially considering the last video that I just created for you, that Venus in the Ptolemaic system can only possibly go through a new phase and crescent phase. It never gets to quarter, as we discussed. It certainly never gets to gibbous or full. So your best answer here is choice A. Okay, so Ptolemy, not only did he have to deal with the strange motions of, say, Venus, as well as, say, Mercury. Mercury was so close to the sun, and he really couldn't observe it too well, because it's not really visible in the nighttime sky. Mars, however, he could view quite well in the nighttime sky, and I'm sure he noticed that, first of all, it had to be farther away from the Earth than, say, Venus was, because it was moving less with respect to the background stars. That's, I'm sure, partly why he decided to put Mars further out in his little concentric circles. But he also had to deal with the fact that Mars also appeared occasionally to slow down, stop, and even reverse direction, what we call retrograde motion, with respect to the background stars. So how to explain it? Also epicycles. Again, using this epicycle, he could explain the fact that Mars was not, appeared to not be going under uniform motion. Of course, if you put the epicycle in there, yeah, it seems to be moving at the same speed around that little epicycle circle. It's just that uniform motion does not appear to be uniform when viewed from the Earth. But again, it was a geometric device that seemed to work approximately well at that time. And so that's why it wound up holding sway for many centuries. Okay, so just in case you think I'm lying to you about this retrograde motion stuff, I wanted to actually walk you through an activity that I do with my traditional classes using Stellarium. So remember, Stellarium is this downloadable planetarium program that allows you to essentially look at the sky anytime you want, from any location you want, etc., etc. So I'm recording this in December of 2015, and I know that Mars is going to go into retrograde motion in a few months. So I'm actually going to show you how to demonstrate that using Stellarium. The first thing you want to do, of course, is we want to find Mars. So I haven't part of the program you can find it. Oh gosh, it's actually below my horizon today, and so therefore I'm going to have to turn off my ground. And you can do that. There are little tools here. You can turn off the ground. You can also turn off the atmosphere, which allows us to see the stars night or day. And so sure enough, there's Mars. And another thing that'll be useful is for me to actually, in this activity, throw on my constellation lines. I might even throw on my constellation labels, just so that I can see where Mars is with respect to the background stars right now. Now, the only thing you have to do is just start advancing time but kind of you might want to do it in days. So notice I'm going to start in, it's 1 o'clock in the afternoon, almost 2 o'clock in the afternoon on December 15th, 2015. I'm going to start advancing it day by day. So notice that tomorrow at the same time, Mars will have moved a little bit eastward with respect to the background stars. And I'm going to go, so it's in Virgo right now, but as we get into January, especially late January, it's going to be moving into Libra. But again, it's going to be moving eastward with respect to the background stars. Except when we get into March, notice what happens. It slows down. As it gets into Scorpius, it actually slows down and changes direction. It appears to be moving now westward with respect to the background stars. It's going to move through Libra again. And then as we get into July of 2015, it now starts to move eastward again. It's going to get back into Scorpius, etc., etc. So that's a good example of retrograde motion. We can actually see it when we use Stellarium, or really any planetarium program you choose in order to show that off. Okay, so again, you may want to pause this and think about it before you hit play again and listen to the answer. The question is, how did Ptolemy account for the retrograde motion? Again, the retrograde motion was a problem because he was a classical astronomer. He thought these ideas of perfection of the heavens, the sense that everything moved in perfect circles and that things moved uniformly. They never changed speed. So that was a real problem when he actually saw these planets appearing to change speed. So what are our options? Well, could they slow down, stop, and reverse orbital direction around the sun? Well, choice A would be no, because first of all, he didn't think that the planets went around the sun. He thought that the planets went around the Earth. This is a geocentric model of the universe. And certainly he wouldn't want the planets to be slowing down or stopping, because that would be non-uniform motion. So we can discount A. We can discount B. Again, it refers to orbiting the sun. They don't orbit the sun, at least not in Ptolemy's model. And so therefore, C looks like a possibility. D, the sun and moon orbit the Earth, whereas all the other planets orbit the sun. Again, that would not be part of the geocentric model. The geocentric model means that everything goes around the Earth. So really, only C is the possibility here. That's why he came up with this system of epicycles, because geometrically it gave him essentially the right answer. He still had a hard time really explaining or predicting all the motions of the planets, but the epicycles were at least a start for him. Now, it wasn't until nearly the early 16th century that Copernicus finally came along and had a different theory, different hypothesis for why the planets appeared to move the way they did. And it was a very radical model, because he said that, gosh, let's not have the Earth be the center of the universe. Let's let the sun be the center of the universe. That's what's called the heliocentric universe. And by using this, Copernicus was essentially saying that Ptolemy's system was just too cumbersome. All these crazy epicycles, it wasn't simple enough to really be the correct explanation. That Copernicus could explain this apparent retrograde motion much more simply by putting the sun at the center of things. And so therefore you have essentially the Earth going around the sun and a planet such as Mars going around the sun. And because the Earth is closer to the sun than Mars, it's kind of like sprinters or runners going around a track. So the Earth is going around the sun on an inner lane compared to the orbit of Mars. And therefore, the Earth is actually going faster. It's going to pass Mars as it goes around on the inside part of the track. And therefore, when you start to look at Mars with respect to the background stars, it will appear to move generally eastward for most of the time, but occasionally when the Earth is actually passing it, it will appear to stop and then actually reverse direction and move westward with respect to the background stars, which is what Ptolemy had observed, as well as Copernicus had observed as well. But this is a much simpler, or at least to Copernicus, seemed like a much simpler explanation, putting the sun at the center of the universe rather than the Earth. Okay, so let's actually see some retrograde motion in action. Again, this is according to Copernicus's heliocentric model. Notice that the sun is indeed here at the center. There's the Earth. There's Mars. And notice that right now, when viewing Mars from Earth, Mars appears to be essentially in the direction of, this is Leo the lion. You can see this little backward question mark. That's the head of Leo, and this little triangle back here is essentially the hindquarters of Leo. So right now, in this orientation, the Mars appears to be located close to the hindquarters of Leo. Now, as I hit start, notice what happens with the relative positions of the Earth and Mars and how that changes the angle at which Mars is viewed from the Earth, and that's going to, of course, change the position of Mars with respect to the background stars. Again, most of the time, all planets move eastward with respect to the background stars, but on occasion, the planets appear to move retrograde, meaning westward with respect to the background stars. So again, initially moving eastward, but now as Earth passes Mars, Mars appears to slow down and then move westward with respect to the background stars for a time period until it then again stops and resumes its eastward motion. Again, this is all due to the changing relative positions of of Earth and Mars as they orbit the Sun. Copernicus's heliocentric model of the universe. Notice this is the same question from a couple of slides ago, the only difference being that now we're asking about Copernicus instead of Ptolemy. How did Copernicus account for retrograde motion? Because they were both trying to explain the same physical phenomenon. They both observed this retrograde motion. It was a matter of whose explanation would make more sense. And Copernicus's turns out wins the day in the grand scheme of things because it was a simpler explanation. But it wasn't perfect, as it turns out. Copernicus, even with his heliocentric model of the universe, could not predict the positions of the planets perfectly. And that's always the beauty of a scientific theory. A lot of people don't really understand what theory means in science. A theory is not just a wild guess. It's not even an educated guess. A theory is a framework which explains observed phenomenon. So both these guys were observing the fact that, yeah, the planets appear to be moving backward and slowing down and all this kind of stuff. So the theory is the framework. It's how they explain it. And so both of these guys could explain, using either epicycles or heliocentrism, they could explain how this weird motion of the planets could possibly be. The next test of a good theory is if it has predictive capability, meaning if things are the way Ptolemy says, or if things are the way Copernicus says, could you predict the future positions of planets according to these theories? And it turns out that neither one was really that good at predicting the future positions of the planets according to their theories. So these were not perfect theories, and it turns out both had to be, well, Ptolemy's was completely discarded. Copernicus's had to be modified, as we're going to find out. But anyway, how did Copernicus account for the retrograde motion? Well, it wasn't A, because again, he didn't think that the planets orbited the Earth. He thought the Earth and all the other planets orbited the Sun. So throw out A, throw out C. Epicycles, that was Ptolemy's territory. That was what Copernicus really had a problem with. And also notice that in D has the sun and the moon orbiting the Earth. That's geocentrism. It's not heliocentrism. So therefore B is our best answer here. All the planets, including the Earth, are essentially runners on a track, with the inner planets moving faster and therefore passing the outer planets and therefore changing the angles and making the outer planets appear to move retrograde. Okay, so now what of Aristotle's universe was included in Copernicus's model? Well, it turns out that certainly it's not A, because Aristotle was indeed geocentric. Copernicus was proposing something entirely different, heliocentrism, so Earth would not be the center of the universe. B, that was not part of Aristotle's model. Aristotle did not say that Mercury and Venus move around the Sun. He thought Mercury and Venus moved around the Earth. C also would be more geocentric, so we can throw out A, B, and C. D, notice that even with the Sun at the center, one thing that Copernicus retained from the Aristotelian model was the fact that all those planets appeared to be moving with uniform circular motion around the Sun. That turns out to be a problem, but it certainly fit with Aristotle's notion of the motion of the heavens. So D is indeed the correct answer here. We'll talk about elliptical orbits in a few minutes. Okay, so the next interesting character in astronomical history is a fellow named Tycho Brahe, sometimes just referred to as Tycho. And he followed fairly closely on the heels of Copernicus. He was certainly aware of Copernicus, he was certainly aware of Ptolemy, and he wound up kind of trying to maybe bridge the two. His biggest contribution was the fact that he essentially had the most sophisticated measuring instruments of his time. They were not telescopes, but he was able to measure and document the motions of the heavens with great accuracy. And he did spent like 20 years taking copious observations. Now he had a problem with, well, certainly he had a problem with Ptolemy, because Ptolemy had a lot of inaccuracy, but he also had a problem with the Copernican model of the universe because he didn't see any parallax shift in the background stars. So he desperately held on to the geocentric model. So the heliocentric had not yet won the day. And was not fully adopted at this point. And so Brahe was a geocentrist who had the Earth at the center, but had a slightly different view than Ptolemy, in the sense that he had the sun orbiting the Earth, and then the planets orbiting, most of the other planets orbiting the sun, and then of course the background stars orbiting the Earth. So it was a relatively unusual system that Tycho had worked up. Okay, so I think I essentially just kind of gave you the answer to this one. Brahe was pre-telescope days, and so therefore he did not have any kind of special equipment except for this essentially special chair that he had built. And his biggest, most important contribution was not the model. Even though his model was kind of part Aristotelian and part Copernican, that's not the lasting contribution, because that's not what we currently have. That certainly was part of his worldview, but it wasn't a very important contribution because it eventually would be discarded. What he contributed was the measurements of planetary positions. He did have he discovered a supernova. It was called Tycho's nova, new star, but even that was not as significant as the amount of data that he was able to provide to our next character in the story, Johannes Kepler. So Kepler inherited a lot of Brahe's data, and he was the first person. He was a mathematical genius, and he was able to apply math to all this data. But the one thing he had to do, the true insight that Kepler had, was that all those thinkers ahead of him were wrong in assuming that the heavens moved in perfect circles. He said that in order to explain how the motion of the planets, they couldn't be moving in perfect circles. They had to be moving in what are called ellipses, essentially flattened out circles, and of varying eccentricities. So the eccentricity of an ellipse is defined as being the distance of the center to one of the foci, because there's a focus of an ellipse in two positions, and the distance of the center of the ellipse to a focus is what's called C, and the distance from the center of the ellipse to the farthest point of the ellipse is what's called the semi-major axis, A. And to describe the eccentricity of an ellipse, you divide the C value by the A value, and it gives you the eccentricity. Now, when your focus is right in the center, and the C value is 0, you have a perfect circle. So an ellipse that has an eccentricity of 0 is a perfect circle. The larger than your eccentricity value, the more out of round your ellipse is. And just to make the point then, here is an eccentricity demonstrator which allows me to change. I can change the size of the semi-major axis. And notice that when you have an eccentricity that's close to 1, you've got a very eccentric kind of ellipse. And of course, if I change the distance from the center of the ellipse to one of the foci, as I decrease that down to 0, then I wind up with a perfect circle. So this is not unlike the Earth's orbit. The Earth's orbit is almost perfectly circular. It's slightly eccentric, and I forget the exact value of its eccentricity, but it's almost perfectly circular, but slightly out of round. So the larger your eccentricity, the more out of round your ellipse is. Okay, so as I've already mentioned, Kepler's one of his big changes was that he no longer assumed that the heavenly bodies moved in perfect circles. He said they moved in ellipses. So that certainly would be choice A. But one thing that I also didn't mention is that, of course, an ellipse, unlike a circle only has a center. An ellipse actually has two foci. And what he realized was that not only in Kepler's first law of planetary motion, not only do the planets move in elliptical orbits, but the sun is at the focus of one of that ellipse. He said the sun is at one of the foci of the elliptical orbits of all the planets. Okay, following from the first law of planetary motion, Kepler realized that because the planets no longer moved in perfect circles, but rather in elliptical motion, that would also mean that they would not be moving at the same speed all the time. They wouldn't have that uniform motion that had always been assumed. They could actually move at different speeds. So that when the planet was closer to the sun, it had to be moving faster. And so essentially what he says is that a line from the planet to the sun sweeps out equal areas in equal intervals of time. This area here is what's called a solid angle. So if you could, and imagine this is a very unround piece of a big old unround pizza pie. What Kepler says is that the amount of, let's say not only is it out of round, but it's really poorly cut. What Kepler's saying is that this area, this amount of pizza, if you were to eat this piece of pizza, you'd be eating the same amount of pizza as if you ate this piece of pizza. So what he's saying is that a planet should sweep out an equal solid angle or an equal area in equal amounts of time. So if a planet goes this far from A to B in 1 month, it would sweep out this amount of area. And similarly, if it moves from A prime to B prime, it has to move this far in order to sweep out an equal amount of area in 1 month. So a line from a planet to the sun sweeps out equal areas or equal solid angles in equal intervals of time. Very, very important insight. And then, of course, the third law of planetary motion that Kepler figured out was that there was a relationship between the time that it takes a planet to orbit the sun and its distance from the sun. And it's given as this: p squared, the orbital period, the amount of time it takes for the planet to orbit the sun, in Earth years is equal to the distance of the planet from the sun in AUs. Remember, an AU is an astronomical unit cubed. So a pretty simple mathematical relationship that relates the orbital period of a planet to its distance from the sun. Okay, so Kepler's second law, remember, is the one that relates the solid angle swept out by a planet orbiting the sun in equal amounts of time. And hopefully in the previous slide you can notice that the planet moves a smaller distance from A to B than it does when it goes from A prime to B prime. Remember that speed is equal to distance divided by time. So we said that both of those planets were moving equal times, 1 month. But from A prime to B prime, it moves a much larger distance, and therefore its speed must be much larger at that point in its orbit compared to when it's farther away from the sun. Okay, so recall that Kepler's third law relates the distance of a planet from the sun with its orbital period. And it's a relatively simple mathematical relationship. P squared equals A cubed. So let's take, for example, the Earth. How far away is the Earth from the sun? You should know this. How many AUs is it away? Well, by definition, it's 1 AU. So how long is the Earth's orbital period? Well, sure enough, 1 year, 1 Earth year, because 1 squared equals 1 cubed. That's pretty simple. Now, do you know your other planets? Do you know them in order starting from the sun? Remember, I told you to do that in Module 1. Do you know how far, let's say, Mercury is from the sun in AUs? Well, it turns out, is it less than 1 or greater than 1? It's got to be less than 1, right? Because it's closer to the sun. So sure enough, it's actually about 0.4 AUs. So what's its period? It's about 0.25. 0.25 years, about a quarter of a year. And sure enough, the orbital period of Mercury is around 88 days. And you can play the same game with the rest of the planets. How far away is Venus from the sun? 0.7. How long is its year? About a half an Earth year. How about let's take Jupiter. Well, let's just go through them all. We've already done the Earth. How far away is Mars? Mars is about 1.5 AUs away from the sun. Now go out to Mercury. I'm sorry, go out to Jupiter. So a Mars year is about two Earth years. How about Jupiter? It's 5 AUs away from the sun. Therefore, for it to go around the sun one time, about 11 years is how long it takes. How about Saturn? 10 AUs takes 31, almost 32 years for Saturn to go around the sun one time. How about Uranus? 20 AUs out? About 90 years, 89 years. And finally Neptune, 30 AUs out, takes 64 years to go around the sun one time. Okay, then after Kepler along comes Galileo, and Galileo made many, many contributions, not only to astronomy, but also just to science in general. He did not, however, discover the telescope, but he was one of the first to put the telescope to use in observing the night sky. So some of the very important discoveries he came up with, of course, he discovered the Galilean moons, Io, Europa, Ganymede, and Callisto, and he actually tracked them. And he started to notice that, okay, this was another support for the heliocentric model. He started to notice that there are moons that are orbiting Jupiter. So that would not make a whole lot of sense if the geocentric model was correct. If everything was supposed to orbit the Earth, then what the heck were these moons doing orbiting Jupiter? So again, this was a nail in the coffin, but not the definitive nail. He also noticed the rings of Saturn, even though he didn't know what they really were. Most importantly, however, as we're going to discuss, he noticed that Venus, by putting a telescope on it, went through phases. Again, with the naked eye, Venus just looks like a bright dot. But through a telescope, you can actually see the disk of Venus. And he noticed that it went through not just the crescent phases, not just the new phase, but also gibbous and full. Those were the final nails put into the coffin of geocentrism. So Galileo was indeed swinging a hammer. The question is, whose nails was he hammering in the coffin? Well, it turns out that Galileo was, of course, supporting the Copernican model of the universe, the heliocentric model of the universe, and therefore he was doing away with the geocentric model, which was proposed by both Aristotle as well as Ptolemy. Both of those guys were geocentrists, and therefore your proper answer here is D. Yet another flaw in classical astronomy that Galileo brought to light, pun intended, was the fact that the sun, which was thought to be perfect, remember this idea of perfection that ruled the classical mindset, when Galileo put a telescope on the sun and viewed the sun, he noticed that there were spots on the sun. It had blemishes, which is certainly something that's far from perfection. And these blemishes changed, right? They changed in number and position and that sort of thing. So the sun, which was thought to be perfect and unchanging, sure enough was changing. That, again, yet another nail that Galileo drove home. Okay, so I've told you that Venus goes through all of its phases, not just the crescent phase and the new phase. Do you believe me? You shouldn't, right? You shouldn't take anything on authority. What you should do is seek out tools or seek out evidence, and you have the tools at your disposal. Here's Stellarium, right? Good old Stellarium. Never forget about it. Or any, like I said, any planetarium program will do. What can we do to prove that Galileo was correct? Let's go ahead and find Venus. And again, it's below my horizon. Well, can I correct that? Sure. Let me just turn off my ground. Let me turn off my atmosphere so I can see it during the daytime. There's Venus. What I'm going to do is I'm going to zoom in on Venus. Let me get a closer look at Venus. And so today, here we are in mid-December 2015. Venus is in its gibbous phase. So that in itself proves that Galileo was correct, that Copernicus was correct, and that the geocentrists were not correct. Because remember, the Ptolemaic model, Venus cannot possibly be in a gibbous phase. Now, what else can I show off since we're here? Let's go ahead and change the dates. Let's just go ahead and take it forward in time. And notice as I take this forward in time, we'll be viewing Venus now. We're into January. And again, notice it's getting more and more gibbous until eventually I'll wind up with a full Venus. Now I'm stepping it through day by day. I can speed this up by going month by month. So notice in June, it's going to be a full Venus. Now notice we start to get a gibbous Venus. Until now I start to get to I'm going to need to back out a little bit. Now in February to March of 2017, I went with a crescent Venus. And then in April, crescent, back to quarter, and then back to gibbous Venus. All right, so indeed, Galileo was indeed correct. And we know that not because Galileo said so, not because Mr. Swanson said so, because we have proven it to ourselves using the tools at our disposal. Evidence via Stellarium. Okay, so now that we know that indeed the heliocentric model is correct, another thing, and we've already talked about the phases of Venus, you should have at least a little bit of a feel as to the required geometry of Sun, Venus, and Earth in order to produce these different phases. So let's pretend that planet 1 is the Earth, because it's farther out from the Sun than Venus is. Remember that the Earth is 1 AU away. Venus is only 0.7 AUs away from the Sun. And so we're going to let Venus be 2, and obviously the Sun is going to be at the middle. So the question is, can you remember how you figured out the different phases of the Moon? Hopefully the bisector method was the most effective. So essentially, pretend that half of Venus is illuminated. The side that's facing the Sun is illuminated. The side that's facing away from the Sun would be dark. And the question is, if you were viewing from the Earth and viewing Venus, can you bisect Venus and think about what it should look like? Well, if you're viewing Venus from the Earth, you would see the right side essentially almost halfway lit up. You'd be seeing the right half of Venus being lit up and the left side being essentially dark, which is what the view we see here down at the bottom. Planet 2 is seen from planet 1. So we're seeing essentially a crescent Venus. And it turns out that, yeah, anytime that Venus is essentially between the Earth and the Sun, it's essentially in its crescent phase. In fact, when it's directly between, it's in its new phase, because notice that you'd be seeing the unilluminated side of Venus from the Earth. That's new Venus. And even on this side, it's still crescent, just the other side is lit up. And again, you should be able to use the bisector method to prove that to yourself. And notice when the Venus gets to this position, now it's getting into gibbous Venus. And again, this is only possible in the heliocentric model when Venus is between the Earth and Sun. So eventually you get to full Venus, gibbous Venus, and then back to crescent Venus. Okay, welcome again to my office. This is indeed my office. This is not a bathroom. However, I wanted to share with you a little bit about my bathroom routine. Here I've got a roll of toilet paper. Now, when I'm in the bathroom, quite often I take some reading material with me, and I've got one hand with the book, and I'm taking care of nature's business, and so I only have one hand free with which to take care of the toilet paper, right? So what do you do when you have that situation where you've only got one hand and you've got to rip off some toilet paper? You do one of those deals, right? When you do that, you are essentially using Newton's first law of motion, sometimes called the law of inertia. Inertia has to do with mass. The greater the amount of mass, the greater amount of inertia. The less mass, the less inertia. Vice versa. Essentially, inertia and mass are synonymous. So what happened there? Well, notice when I pull off a little bit of toilet paper, this little tail here, there's not much mass. There's a couple of sheets of toilet. That's not much mass. So right now that toilet paper is at rest. The tail and the entire roll is at rest. But when I apply a force, I can, because this doesn't have very much mass, I can make it move quite easily. So an object at rest will remain at rest unless acted by an outside force. But it turns out that when there's not much inertia there, my force can cause a lot of motion. Whereas the rest of the roll has a lot of mass, a lot of inertia. So despite the fact that I was applying a force, it didn't have much impact on that large mass. And therefore, essentially what happened was my tail moved more than the roll moved. And therefore, that's what made it tear. Happy Newton's first law to you. Okay, this is the slide that I get a chance to make the case for Newton's second law of motion. Everyone knows Newton's first law. Object at rest stays at rest, right? You've all heard that one. You've probably also heard the third law, which has to do with action-reaction. For every action, there's an equal and opposite reaction. Heard that before? I bet you have. That's Newton's third law. We're not there yet. Newton's second law, which to me is the most important of the bunch, doesn't stick in your head because it's wordy, right? Read this law of acceleration that's on the screen here. It's got a lot of stuff to it. So I like to think about it. I kind of break it down first of all. Let's look at that first clause. The acceleration produced by a net force on an object is directly proportional to the net force. That's kind of wordy and mathematical. What it's saying, and I call this a Fonzie law. This is a 1970s reference. This, right? Is that when the force goes up, the acceleration goes up. They're directly proportional to each other. Hey. If you don't like that, if that reference means nothing to you, let's think about something a little more updated, even though it's getting a little dated. I'm going to call this the notorious BIG law. Mo money, mo problems, right? Directly proportional, right? When one goes up, the other goes up. When then one goes down, the other goes down, correct? That's the first part of the law of acceleration. The acceleration will go up if the net force goes up. Now let's look at the second clause. It says the acceleration produced by a net force on an object is inversely proportional to the mass of the object. This is what I call a Siskel-Ebert law. Remember, Siskel and Ebert were movie reviewers who came up with the whole thumbs up, thumbs down movie review system. Their show was most entertaining when they disagreed, when the one guy liked a movie and the other guy didn't like a movie. That's why I call this the Siskel-Ebert law. It turns out when your mass goes up, your acceleration goes down. They're inversely proportional. That's why I call it a Siskel-Ebert law. When the mass goes up, the acceleration goes down, or vice versa. When the mass goes down, the acceleration goes up. They are inversely proportional to each other. Okay, to explain Newton's third law, which everyone at least is familiar with, for every action there's an equal and opposite reaction. I usually illustrate it by punching walls, but my camera is too far away from a wall, so well, I'm going to substitute the wall with, I'm going to punch a book. And the book, to be honest with you, has had it coming for quite a while. So let me punch this book. Great. How do I know I punched the book? Well, because my fingers kind of hurt there. My fingers don't normally hurt, but all of a sudden I came into contact with this book, and all of a sudden my hand hurt. Turns out I can't hit the book without the book hitting me back. And in fact, when I punch harder, it hurts more, right? Well, why is that? Because I exerted more force on the book exerted more force on me. For every action, there is an equal and opposite reaction. It's equal in magnitude and opposite in direction. I hit the book in this direction, the book hits me in this direction, causing my hand to stop and also causing my hand to hurt. Okay, one last final illustration about Newton's third law. Now we talked about action-reaction forces. Let's take, for example, this little plasticware lid, and I'm going to punch it. I think I've got anger issues. When I exerted a force on the lid, remember it was essentially stationary, all of a sudden, boom, it accelerated, didn't it? In fact, it accelerated quite a bit. Well, why was that? Because I exerted a force on it, right? I exerted a certain force. I'll call it, let's see, force of punch. And that was the same, didn't you remember from Newton's third law, the force that I exert on the lid must be the same as the force that the lid exerts on me, correct? So, therefore, the force of punch, let's say the force of the punch on the lid, I'm going to put FPL, has got to be equal to the force of the punch on my hand. I'm going to put FPH. That's Newton's third law. Now, let's talk about the acceleration on each of the objects. Let's talk about the acceleration. So remember, from Newton's second law, a net force, and the only force that was acting on that lid really horizontally at least was the force of my punch. That's what caused the acceleration. Well, why did it accelerate so much? Because it was the mass of the lid is really, really tiny. So I'm going to make a little m there, and then I produced a large acceleration. I'm going to make a big old lowercase a here. The acceleration of the lid, right? That, remember, Newton's law is F equals ma. So essentially, I'm just rewriting the force of the punch on the lid as being the mass of the lid, which is tiny, times a huge acceleration of the lid. And remember that the force of the punch on the lid must be equal to the force of the punch on my hand. However, what happened to my hand when I punched it? Not much, right? My hand continued, it was moving along at a certain velocity, and it essentially continued along in that same velocity. It may have slowed down just a little bit. Well, why was that? Because my hand is much more massive. So in this case, the mass of my hand, I'll make that big old M of my hand, only experienced a small little acceleration. Yet notice that if I have a big mass and a small acceleration, that can give me the same product as a small mass and a large acceleration. Okay. So another interesting thing is that Newton's third law applies to forces, contact forces, like punches and pulls and frictions and all that kind of stuff, but it also applies to forces at a distance. For example, gravity, right? I hold my apple up. I let it go. Well, what's going on there? Why does the apple fall to begin with? Because there's a force of the earth pulling on the apple that we call weight, right? So the earth pulls on the apple with a force we call weight. But didn't we just say from Newton's third law that you can't have one force without another force? So if the earth pulls on the apple, doesn't the apple pull on the earth? You betcha it does. So then you might ask yourself, well, why do I see the apple? And I understand from Newton's second law that, okay, the earth pulls on the apple, and that means there's a force there, and in fact, it's an unbalanced force, and that's what causes the apple to accelerate. In fact, I can figure out the acceleration of the apple by, so acceleration of the apple is equal to the weight of the apple. Again, we're not really considering air resistance at this point, divided by the mass of the apple. Again, this is going to be Newton's second law just rewritten. So, well, what's the weight of the apple? Isn't that just the mass of the apple times g? And of course, I'm dividing by mass of apple, and so you can pretty clearly see that yes, my apple should fall at an acceleration of g. That makes sense. However, shouldn't my Earth accelerate as well? Isn't my Earth being acted upon by a force? What if I look at the forces acting on the Earth? Well, in this case, I say, okay, well, let's see, what's the acceleration of the Earth? Put A with a little e there. Let's see, the force is the force of the apple acting on the Earth, which is the same, remember for Newton's third law, for every action there's an equal and opposite reaction. So the force that the Earth pulls on the apple with, downward, which we call weight of the apple, must be equal to an opposite in direction as the force of the apple acting on the Earth. So it turns out that my numerator here, the net force acting on the Earth, is still the same. It's essentially the weight of the apple divided by the mass. Now it's not the mass of the apple, it's the mass of the Earth, because I want to figure out the acceleration of the Earth. And so we wind up with, we rewrite mass of the weight of the apple as mass of apple times g. But now notice we're not dividing mass of apple by mass of apple. We're dividing the mass of the apple by the mass of the Earth. And you can figure out the mass of the apple compared to the mass of the Earth is such a tiny fraction. That's why essentially the acceleration is so small that it's negligible. You couldn't see it, you certainly couldn't measure it, much less see it. And that's why Newton's third law still is upheld in this situation, but we're dealing with the same force acting on really different masses. The mass of the Earth is so huge that the acceleration of the Earth is essentially negligible. Okay, so Newton's law of universal gravitation. You've probably heard the legend of Newton sitting under an apple tree and getting hit in the head with the apple. What he realized was that the force, whether or not the legend is true or not, he realized that the force that causes an apple to fall from a tree is the same force that causes the moon to remain in orbit around the Earth as opposed to flying off in a straight line in space. All things attract each other. If they've got mass, they're going to attract each other, and he actually came up with the mathematical description for that attraction. And it's very simple, actually. It depends only on the masses of the respective objects as well as the distance between those two objects. Now, which one is the bigger factor? Well, it turns out the distance is, quite clearly. And you're going to see this when you do a little algebra in a couple of slides. But the distance factor is squared, and that becomes a much bigger player then. But one thing you should be able to tell, even before playing around with the math, is that because the distance is in the denominator, increasing the distance decreases the force. So if you have two objects that are experiencing a certain force between them, and if you make them farther apart from each other, the force is going to decrease. When you bring them close together, the force is going to increase. Now notice with the mass values, if either of the masses go up, the force is going to go up. But certainly distance is the bigger player because the distance factor gets squared. Here's a little practice playing around with Newton's law of universal gravitation. Again, from the way I introduced it, you should recognize that the gravitational force experienced between two objects is directly proportional to the product of their masses and indirectly proportional to the square of the distance between them. So what does this all mean? So let me just imagine that I've got two objects. Each of them have a mass of 1. That's what this 1, 1 stands for. Each of them has a mass of 1, and they're separated by a distance of 1. And again, we don't really care about the units here, some arbitrary unit. So they've got a mass each of 1 and a separation between them of 1. And that winds up, I wind up with a force of, let's say, 1. Now what happens if I make one of the objects twice as massive? I leave everything else the same except for I make mass 1. Let me go ahead and double it. Notice what happens to the force that each one experiences. Notice that it doubled, didn't it? Right? It went from being 1 to 2. What if I triple it? I triple the force that each one experiences. What if I triple the mass of the first one and I double the mass of the second? Notice that I wind up with a force between them that is the product of the masses of each. Now, let's set it back to where we started. What if I left the masses at 1, but what if I cut the distance between them? What if I bring them closer together? What if I cut the distance between them in half? Notice what happens. I wind up with 4 times the force. Well, why is it? Why is that? Because 1/2 squared is 1/4. And since 1/4 is in the denominator, it winds up quadrupling the overall fraction. So this is how the basic algebra goes on with Newton's law of universal gravitation. On the next slide, you're going to see slightly more complicated, what appear to be more complicated calculations, and that's just because the actual values are used. Instead of just using arbitrary mass units and arbitrary distances and ignoring this value for g, which is just a constant, all that stuff is thrown in there, but the same main story remains, that the gravitational force acting between two objects is directly proportional to the product of their masses and indirectly proportional to the square of the distance that separates them. Okay, so you may have noticed that I spent a lot of time in the previous couple of slides talking about Newton's laws of motion, and they're really not even explained very well in your textbook. I think the textbook author assumes that you have taken some sort of a physics or physical science course in the past, and you may not have, and that's why I spent a little bit of time talking about the laws of motion. The one that's most, the law, Newton's law that's most important to astronomy is the law of universal gravitation, but the laws of motion are kind of build into it or apply, and therefore I wanted to go over that. But anyway, here is the law of gravitation. And goodness gracious, isn't it a mess? And there's a lot of stuff there. But here's the most important part. The gravitational force that any two objects exert on each other is essentially calculable using this equation, g m1 m2 divided by r squared. Forget about the g. The g is just a constant, so we don't really care about it. It is important that we understand that the force that any two objects experience is related, it's directly proportional to the product. That means the multiplication of their masses together. And it's also dependent upon the distance between them squared. Of course, notice that's in the denominator, which means that when that denominator gets big, the overall fraction gets small. It's just like if you started out with a fraction that was 1/2, and then you started to increase the denominator, make the denominator, instead of making it a 2, make it a 4 or a 6 or an 8 or a 12. The overall fraction gets smaller and smaller. That's what happens in this relationship. So right now we've got the gravitational force between a person and the Earth. And of course, it's the person who's standing on the surface of the Earth. What's the gravitational force that that person experiences? That's what we actually call weight commonly. And of course, the person standing on the surface of the Earth, so therefore the separation of the person's mass and the Earth's center of mass, which we assume is at the center of the Earth, the distance there is about 6 million meters, which is more commonly referred to as about 4,000 miles. That's how far we are from the center of the Earth. So now notice when you put in those values, the mass of the person, the mass of the Earth, the distance between the Earth and the person squared, you wind up with a total of about 700 newtons. 7 times 10 to the second is 700 newtons. Newton is a unit of force in the metric system. Now, one thing that's cool about this simulation is it allows me to double the mass of, let me double the mass of the person. Notice what happens to the force between the two of them. Notice it went up to 1,400. It was 700, now it's 1,400. So it doubled, right? By doubling the mass of the person's weight doubles, essentially. Same thing, what if I double the mass of the Earth? Notice by doubling the mass of the Earth, I get the same result. The force between the two objects goes from 700 to 1,400. So notice that by doubling either of these masses, I double the force. And that makes sense mathematically. What if I change the radius? What if I make the radius of the Earth twice as large? Remember, my force right now is 700. Now I'm going to double the radius of the Earth, and notice that my value now is 170 newtons. It's not half, right? It's less than half of 700, because it turns out that by doubling it, that doubling gets squared, and therefore this winds up being a bigger change. So of the two, radius is more important when it comes to the force that two objects experience gravitationally. Now, as you hopefully learned in Newton's third law, the force of attraction that the person feels due to the Earth must be equal to an opposite direction of the force that the Earth feels due to the person. So again, for every action, there's an equal and opposite reaction. I can't hit a book with more force or less force than the book exerts on me. Same thing, the Earth can't pull on a person any more or less than the person pulls on the Earth. And yet, if you jump up and down, you can feel gravity pull you back to the Earth. You don't necessarily feel the Earth being pulled by your own gravitational field. Well, why is it? That's due to Newton's second law, which is worked out here. So each of these objects experiences the same force, but they don't experience the same acceleration. Why not? The force is the same. The numerator in both these equations are the same. This is Newton's second law written in equation form. Acceleration of an object is directly proportional to the net force acting on that object, and indirectly proportional to the mass of that object. So the acceleration that a person feels, A1 here, is the force, which is 700 newtons, divided by the mass of that person. which winds up being 9.81 meters per second squared. So a person, if they're falling near the surface of the Earth, is going to fall at 9.81 meters per second squared. That's a pretty large acceleration. What about the acceleration of the Earth due to that same force? Remember, the numerator stays the same. It's 700 newtons divided by the mass of the Earth, which is huge, 5.97 times 10 to the 24th. And therefore, yes, the Earth experiences a small the Earth experiences the same force, and yet winds up with a much smaller acceleration because it is so much more massive. Now, if you've examined the equation from the previous slide very carefully, again, that's Newton's law of universal gravitation, you will notice that gravity decreases as you get farther away from an object. In fact, it decreases as 1 over the distance squared. That's the relationship. It's an inverse relationship. So as the distance increases, the force decreases, but it never goes to 0. Even when your distance is really large, technically there is a small, tiny little force there. So if you've ever been tempted to think that the reason that astronauts appear to be weightless in space is because there's no gravity in space, think again. And you should be able to confirm this to yourself by just looking at this graph here. This graph is going to be useful in a couple of slides when I recommend that you check out the weight on other planets skill builder. So if you want to drop a few pounds, it turns out all you have to do is get a little bit farther away from the Earth's center. Just climbing Mount Everest will actually make you weigh less. Why is that? Because your mass has not changed. The mass of the Earth has not changed. However, the distance between you and the center of the Earth does increase. Like I said, the distance between the Earth and the center, the Earth's surface and the Earth's center is about 4,000 miles. Mount Everest is 5 miles high, so you would actually be 4,005 miles away from the center of the Earth when you're on the top of Mount Everest, and that will affect the gravitational force with which the Earth pulls on you. In other words, that would affect your weight. Okay, so now this is going to be a question that's going to utilize Newton's law of universal gravitation. So as we know, the force the gravitational force that two objects experience is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Now again, we don't really care about this constant because it's going to be the same in any of the calculations we do with it. That's going to be the factor is the same, so therefore we don't even need to consider it when we're doing our calculations. Now, let's think about how the force between the Earth and the Sun, what that would be. Well, let's just go ahead and say that the mass of the Earth is 1, and let's say the mass of the Sun is 1. Obviously, they're not the same, but for the purposes of this question, that's fine. So we wind up with 1 times 1 divided by 1 squared, 1. Now, the only difference in the premise of this question is that our fictional planet Q has the same mass. It's identical, but it is a distance of 5 AUs away from the Sun. So therefore, notice the numerator wouldn't change. I could keep my mass of the planet being the same. I could keep the planet of the Sun, the mass of the Sun being the same. But now instead of having a 1 in the denominator, I wind up with a 5 in the denominator. Remember that 5 gets squared. So what's 5 squared? 25. So therefore, the force that planet Q experiences due to the Sun is 1/25. How does that compare to the force that the Earth experiences due to the Sun? It's much, much smaller, right? So therefore, the amount of force exerted on planet Q is 1/25 the force exerted on planet Earth. Okay, so the topic of satellite motion then brings us full circle, pun intended. Remember when I first introduced Isaac Newton, I talked about that legend about him having the apple hit him on the tree, apple from the tree hit him on the head. What he recognized was that the same force that causes the apple to fall from the tree is the same force that keeps the moon in orbit around the Earth. The moon is an object in motion, so according to his first law of motion, that thing should go off in a straight line off into space. But it doesn't. It always stays essentially the same distance from the Earth. It constantly is moving not in a straight line, but in a circle, right? It's circling the Earth. Well, why is that? It's neither going in a straight line away from the Earth, nor is it falling exactly straight toward the Earth. It's not going to crash into the Earth. So it is a projectile. It's a satellite. And whether it's a natural satellite like the moon or a man-made satellite, what happens with satellite motion is that the object is constantly being pulled toward the Earth. Why? Because the Earth has mass. And so there's a gravitational attraction. And so it's that gravitational attraction causing the object to accelerate, but it doesn't accelerate toward the Earth. It doesn't accelerate away from the Earth. It accelerates in a kind of a constant state of falling toward the Earth. But it's also moving very, very quickly away from the Earth, or at least tangentially to the Earth, and therefore it winds up being a circular motion. Now, if you place your satellite at just the right orbit, it winds up having an orbital period that is equal to the rotational period of the Earth. And therefore, if you've got a satellite in space that orbits one time in 24 hours, of course the Earth is spinning one time in 24 hours, so therefore that object would stay in the same spot over the Earth's surface. And that comes in handy, especially for like weather satellites, for cell phone satellites. You don't want to have the satellite moving faster or slower than the Earth because it wouldn't stay in the same location. You want to have that satellite in the same location. For example, for weather satellites, they've got one satellite that just sits out over the middle of the Atlantic. It's called GOES East, and it's constantly monitoring the tropical activity in the northern Atlantic. And that is very, very useful. If that satellite was moving with respect to the Earth, then you would have periods where it wouldn't be seeing the Atlantic. And therefore, you want to put it in geosynchronous orbit so that it's constantly monitoring that part of the Earth. Okay, we just mentioned the fact that the Earth pulls on the moon, keeping the moon in an orbit around the Earth. If it didn't, the moon would go off in a straight line. But as we also know from Newton's third law, for every action there is an equal and opposite reaction. The fact that the Earth pulls on the moon means that the moon must be pulling on the Earth with the same force, just different direction. And the result of the moon pulling on the Earth really winds up being the tides. The fact that the moon, and remember that the force, the gravitational force, as we know according to the law of gravitation, is really dependent upon the masses of the two objects and the distance between. And so it turns out that the moon actually attracts the water on the near side of the Earth a little more than it does, say, the center of the Earth or even the far side of the Earth, because the distance there is a smaller value, and therefore the overall force is larger. We know that as you get farther away, the gravitational force is smaller. And therefore, and because liquid is more fluid, it can move more than, say, solid land can, what happens is the moon creates a bulge of water on this side of the Earth. And of course, it also creates a bulge over here. Well, why is that? Because the center of the Earth is closer than the water on the backside, and therefore it essentially just kind of pulls the Earth away from the water on the backside, and therefore you wind up with a bulge over on this side. And as the Earth spins, as it rotates, any location is going to move into these bulges, and then move out of the bulges, and move into the bulge. And so that's why you wind up with this lunar cycle, this tidal cycle, essentially every 12 hours. Any location is going to move into a bulge. That's going to be high tide. It's going to move away from the bulge. It's going to be low tide. Move into another bulge. That's going to be high tide, etc., etc. Now, as you know, the moon is not the only game in town. We also have the sun to think about. And the sun, though it is farther away, and therefore its distance, the d factor is going to be much larger, it does have a gravitational pull on the Earth. In fact, that's why the Earth orbits around the sun. It doesn't go off in a straight line either into space. Now, it turns out that in new moon phase, as we know, you've got your sun. I'm going to put my sun. Whoop, there it is. So in new moon phase, notice you've got your moon between Earth and sun. But can you tell that in the new moon phase, the moon would be pulling on the Earth's water and creating a bulge over here, and also a bulge on the other side? The sun is going to be doing the same thing. And therefore, you have what's called a spring tide. This bulge, because of the cumulative pull of the moon and sun, winds up being larger than normal. And therefore, you have what's called a spring tide. The high tides are higher than average, and therefore low tides are lower than average. And that's true in both new moon case as well as in full moon case. In full moon case, you got the moon over here, But again, and so it's pulling on the Earth's water, and the sun is also pulling on the Earth's water. It's going to create very large bulges and therefore very large tides. When the sun is over here and the moon is not lined up, but rather is at a right angle to the sun with respect to the Earth, you get what are called neap tides. Neap tides are when the gravitational effects of both those objects, moon and sun, are kind of fighting each other. And therefore, the high tides are not quite as high. Low tides are not quite as low. Those are called neap tides. So really high tides, extreme tides, are spring tides, and not very extreme tides are what are called neap tides.